All right, everyone. So now we have our last talk where Dale Decatur, Richard Liu, and Naman Dinh are going to tell us about geometry processing from 2D image priors.
All right. Hello, everyone. My name is Dale. This is Richard over here, and Naman is joining us on Zoom today. As I said, we're going to be talking about geometry processing with image priors. And you can see some fun little teasers here on the screen. So just a little bit about us. So we're all PhD students at the University of Chicago. We're advised by Rana Hanaka. And so let's get into it with no further ado. Okay. So we can very clearly see the prevalence of data-driven methods in today's world with models like ChatGPT, Claude, NanoBanana, and Gemini. And while applicable in many domains, data-driven methods have shown impressive effectiveness, especially in the text and image modalities specifically. And that's really thanks to the sheer amount of data they have been able to be trained on. However, if you look at the largest natively 3D trained models of the current day, they're definitely like a clear step below these 2D models in terms of quality. And the reason for that is they're sort of fundamentally limited in the fact that they do not have nearly as much data they can be trained on, right? So we have like orders of magnitude more images than we do 3D data. So you can see this example, right? Like the astronaut horse, like barely gets the details, whereas this image is very sharp, very crisp. Love to see it. So interestingly, even these 2D models seem to have a deep understanding of 3D properties, though, right? So recent work has actually looked into this and basically shown that these 2D models trained explicitly for generation actually have pretty good understanding of qualities such as depth, normals, and more. So how can we take this 3D understanding from these 2D models and use it for 3D tasks? Well, first we need to find some mapping between 2D and 3D. And this mapping can be done in many ways. So you can do things like volumetric rendering, ray tracing, and again, the representation you use for this mapping oftentimes depends on the representation you're using in 3D. So for our talk today, we're going to focus on the representation of projection and rasterization, since that's most commonly used with meshes. And the key thing is that once we have these mappings, if we can supervise some image, we can then translate that to supervision in 3D. So what are some of the challenges when converting between 2D and 3D? So first is this issue of multi-view consistency. The natural way that we might connect 3D information in 2D models is by representing 3D with multiple 2D views, as we see here on the left. But there's this issue of when you convert from the 2D back to the 3D, you need to aggregate this information into a consistent way on the 3D shape. And doing that consistently between different views is oftentimes not trivial, depending on your task. We also need to deal with the resolution of the 2D prior. So the 2D signals that we're using here are almost universally represented as discrete pixel grids, and we need to be careful in how we go about approximating continuous signals from them. So how do we actually bridge this gap between 2D and 3D? So let's look at some specifics for the projection and rasterization approach we talked about a second ago. So given some 3D object in world coordinates, we first introduce a camera and translate that object's canonical world coordinates instead to be defined relative to that camera, to our camera coordinates. And these are still in 3D. From there, we can then project the 3D coordinates of this object onto the screen space of our rendered image. And then finally, we can rasterize the screen space coordinates to get discrete color values at each pixel. So again, once we have this mapping, we can supervise our 3D task with any 2D signal. And while many such signals exist, today we're going to focus on a couple. So direct pixel values, image feature space comparisons, and just direct pixel gradients. And then more importantly, all of these 2D signals we just talked about are able to be obtained from these 2D models that can be trained on these large scales of data. And we're not reliant on any 3D data for this process with this setup. So just a quick little history. So though the use of these 2D models to inform 3D tasks is relatively new, we can sort of already split the methods into two main schools of techniques. So optimization-based techniques compute gradients on the 2D renders and backpropagate them to the 3D representation. And then back projection techniques directly take the 2D information and just unproject it, reverse this projection, and put it back directly on the 3D shape, maybe with some kind of way to correct this multi-view inconsistency issues we discussed. So jumping into the first group, optimization-based methods. These methods are maybe a little bit less common now, especially for generative tasks, because the optimizations are relatively slow. However, they can still be really useful when the task is not compatible with faster approaches such as back projection, which we'll discuss later. So in order to enable these end-to-end optimization methods, we need a rendering pipeline that is differentiable. So going back to this projection rasterization example, if you look at this first step, the projection is pretty clearly differentiable, right? So it's just a bunch of matrix multiplications to transform our coordinate systems. However, this rasterization step, it gets a little bit more tricky, and it's not obviously differentiable. So it's sort of like, why is that, right? So the issue with rasterization is that the coverage test of whether or not a pixel is covering the object is sort of binary, right? Either you're in or you're out. And this might present some problems, but luckily this is actually a well-studied problem, and people have come up with really effective ways to sort of make this actually differentiable. So essentially, there's lots and lots of details that I'm not saying here, but essentially it's like making these pixel coverage tests as more of a soft boundary with a continuous fall-off. And that way, if you have like a small, tiny change in your geometry, you actually get a tiny change in the pixel value as opposed to an abrupt jump, and then things become differentiable then. So using these differentiable renderers, we can focus on computing some loss directly in 2D. We don't have to worry about 3D anymore. And as we said, this loss can be computed maybe at the pixel level, through feature similarity, which we'll get into later, and then also possibly through some other method that directly produces gradients on the 2D image. And once we have this 2D signal, we can take, you compute some loss in 2D on the image, find our gradients, and then backpropagate them through the render to get our updates in 3D. So let's take a look at that first example of pixel supervision. So so directly computing L2 loss in the pixels is very effective when you have a clear target image that you're trying to optimize towards. Right? If you have the exact target images that match at a pixel level, unfortunately, this is almost never the case. So this is useful sometimes, but really not really used in many methods in practice. So now we're going to move on to image features, which is much more useful. So how does this work, right? So this situation that we just described, where you have two images that might not be directly pixel aligned, is exactly where something like feature similarity can be really helpful. So let's assume you have some pre-trained embedding model that can encode, let's say, both text and images to a joint shared semantic feature space. If we have our initial rendered image, we can then pass it through the encoder to get some feature. And then if we, let's say, have some target text or maybe some target image, but maybe that image doesn't exactly align with what our render looks like, we can also encode that to feature space. Right, and then the important part is that since this model encodes things in terms of semantics, not raw pixels, we can actually make this comparison now, compute some feature similarity loss, and then same thing, just backpropagate it to our 2D image, which then we know can update our 3D representation. So using joint image language embedding models, feature space optimization is seen widespread use for text conditioned 3D tasks such as stylization, generation, and deformation, and more. And additionally, in cases where we are supervising with image targets, this feature space comparison can actually also be really useful. So this is actually a recent work from Richard over here. But basically, the goal is to learn to extract a curve abstraction from a 3D shape that exists. So the way we're going to do this, right, is we're going to render it from multiple views. We'll have these images of the shape, and we want to figure out like what is some curve abstraction of this. And the issue that you run into is that curves and rendered images do not look the same at a pixel level, right? So like, one of them is this very sparse line representation, and the other is dense and colorful. They don't match up in terms of pixels. However, like we just said, you can encode them into feature space and then get these nice little results that you see here because they'll be aligned semantically. So now let's quickly take a look at the final type of 2D signal we're going to talk about, and these are just direct per pixel gradients. So not just computing some loss and then getting the gradients, we're actually just feeding it gradients directly. And the application for this that we're going to talk about is score distillation. So real quick, in past years, diffusion models have seen a lot of success in many areas, but most prominently in image generation. And these models are trained to map one distribution, often Gaussian noise, to another distribution, which might be like the distribution of natural images. And while there are multiple ways to formulate it, for the models we're going to discuss today, we're sort of assuming that they are trained by taking the target images, adding noise to them, and having some model learn to remove that noise. And then people have actually researched how can we, can we take these models that are able to transfer between these different distributions, and can we use that to supervise something like a parametric image representation, which is exactly what our renders are, right? So the way you do this is called score distillation sampling, right? So it does exactly this. So a bunch of works have looked into this, different variations. There's a whole bunch of math. Honestly, some of these papers argue about what is the correct way to represent this, but the most commonly used is the standard score distillation sampling, or SDS for short. And this approach, at a high level, roughly uses the same objective as diffusion model training, in which the model learns weights to move from the noise to the target distribution. However, in SDS, instead of minimizing the loss with respect to the model parameters, you're sort of doing so with respect to the parameters of this 2D image. And this allows us to sort of move our rendered image towards the target distribution. So let's quickly walk through a visualization to try and get an intuition for how this works. So again, first I want to say this is a slightly simplified version of SDS. I'm not talking about like time steps or noise schedules or conditional targets here. But for now, let's just say we start with a render of our 3D representation R. That's going to be in our source distribution. And then, so this is basically a render of our 3D shape, and it's been produced by a differentiable render. And then what we want to do is we want to get some gradient direction that we can apply to this render that tells us how we should move to get towards our target. And this could be like some target condition on text, it could be a condition on some image, whatever we want. So the first thing we do is we add some noise to our existing rendered image R. And this moves it to be more like in distribution of what this model's been trained on. And then from here, we can use the model to map the noisy sample towards the target distribution. Now, what the model predicts is not necessarily this path directly, but it's the noise that if you removed it from RT would give you this path. So really, it's predicting this. So what we can do is we can take the difference of the noise we added, from the epsilon in orange, and subtract out the epsilon predicted by the model, and what we get is this nice direction, which is going to point us towards our target distribution. And this is direction from our actual original rendered image R. So this is basically the direction we're going to use as our gradient in this SDS loss. So can we extend this at all? So one thing we might be interested in is how can we get SDS loss at higher resolutions? So standard SDS actually supervises at, or like the original paper supervised at like 64 by 64 pixels, it was great at the time, but it's also like not super helpful if you're trying to get like super crisp 3D textures or styles or whatever. Right, and this is actually lower resolution than a lot of the image generation models we're used to, so like why is this? Like what is the disconnect here? And to understand how we can address this, we first need to look at how these 2D image generation pipelines typically work. And there are a lot of different ways you can go about doing this, but one popular method is this idea of cascaded architecture. And it's used to increase the resolution of the diffusion models. So what it has is basically a cascade of multiple models in different stages, and like each model is sort of upscaling the result from the previous one. So each stage, so like basically, you know, let's say we have an example here, right? We have like a text prompt for Irish setter. We pass that into the model. We get some 32 by 32 bit output. We take the output of that first model plus the text prompt, feed it back into the second model, and we sort of keep doing this, and we get increasingly higher resolution images. And from there, you know, that's how in 2D image generation you get your high resolution. So can we do the same thing with distillation? And in fact, the answer is yes, but it's interesting because if you look at the original SDS, it was trained on these CDMs, but they only use the first resolution stage. They don't use the other stages, which is seemingly like wasted supervision. So can we use these as well? And to do so, we use this thing called cascaded score distillation, which is essentially the same thing, but it's distilling it from all the stages at once. So how does this work? So if you have some mesh, you can render it at all the different resolutions, so one resolution for each model. And then you sort of independently add noise to each of these. You pass them into the model, and this is like the only step where it's really different. So because the way these models are trained, and we're following the training procedure for diffusion models, for the very top row, this is exactly the same as standard SDS. But for like the middle row, for instance, you can see that it takes not only the image from the noisy image from its resolution, but also the noisy image from the previous resolution as well. And from this, we're going to get predicted noises from the model at all these different resolutions. We can do the same thing. We can compute this difference between the original resolution and the predicted resolution, predicted noise, I mean. And then we get gradients at each of these different resolutions. So we can apply all of these gradients all at once back to our representation. And so does this actually work? Can we actually get better results like this? And the answer is yeah, pretty much. So like here we're showing something, comparing results with CSD and SDS. And for the following prompts, so colorful crochet turtle shell, cactus base, and tiger stripe shirt. And this is the results of SDS. And then if we show the results with CSD, you can see they're like clearly much sharper. So like you can see, you know, on the colorful crochet turtle shell, you get much more clearly interlocking yarn patterns. In the tiger shirt, the stripes are much more sharp. Oh yeah, and here's the zoom ins as well, so you can see those. So yeah, so with that, I am going to pass it off to Naman, who's going to take it from here on Zoom, and we're going to do a little swap on the screen share as well.
Wait, you don't need to swap the screen share. You can, yeah.
Right, we're gonna move it for him. All right.
Okay.
Take it away, Naman.
So a common theme with downstream methods using SDS is coming up with ways to get clean results from such a noisy supervision signal, because it is still a noisy supervision signal. It requires a lot of epochs in your optimization to get a stable convergence. And so what kind of structure and regularization you apply depends on what the task is. And so at our lab, we've come up with methods for various geometry processing tasks, such as texturing, as Dale just showed, as well as geometric stylization and deformation. And so to touch on a geometry processing application, I'll talk about how this is done in my work, Geometry and Style, where we use SDS, or more specifically CSD, to optimize a shape's deformation to achieve some geometric style. The task we want to solve is identity-preserving geometric stylization from a text prompt. And what do we mean by identity-preserving geometric style? You can think of it as imparting medium to high-frequency detail onto geometry, which may include high-frequency geometric texture, like the Lego texture, but also medium-frequency sharp features, flatter or more curved surfaces, more far-reaching than just bump mapping or displacements along the normal, while still retaining the high-level structures of a shape, no massive change in pose or parts. How did we get to this idea, and how do we do this? So our inspiration comes from this paper by Derek Liu and Alec Jacobson, normal-driven spherical shape analogies. The main idea of this paper is to use normals as dictated by a spherical template that maps unit normals to new unit normals. We can see that using a primitive that acts as this template mapping of normals, such as a cube, we can get identity-preserving geometric stylization, such as cubified shapes. But these are limited to simple templates. What if we learned or optimized the normals directly on the shape to be stylized, to get any desired style from a text prompt? And it turns out you can, and just as a peek, here are some of our results. You can see the various styles for the various kinds of chairs which preserve their identity, and the other diverse examples. So how is this done? How do we impose structure onto an SDS-based optimization pipeline to get this type of restricted identity-preserving deformation? On a mesh, the optimization variable of this pipeline is a normal vector for each vertex neighborhood. These normals are used to compute local rotations and then solved into a surface via a differentiable as rigid as possible solve, which we call DARAP, which consists of one local step and one global step. The resulting surface is differentiably rendered, and then SDS, or actually CSD, cascade score distillation, provides loss using a diffusion model given a prompt, as we described earlier. We then backpropagate this loss to update the normals. These normals are first used as the target for a local processes solve, which finds the best rotation matrix, taking a bundle of edge vectors to the same neighborhood, but with the target normal instead of the original vertex normal. You can see that the first term is like a regularization that tries to make the rotation respect the neighborhood. And the second term is what pushes the rotation to turn the normal U towards the prescribed target normal U hat, which we get from the current optimization variable. It has a lambda hyperparameter, which controls the strength of the rotation solution towards the target normal. And then once we've found per vertex rotations, we find the surface that best fits these local rotations. Now, this least squares optimization is just a Poisson equation with a cotangent Laplacian, which means we can use a differentiable solving technique from neural Jacobian fields, which is also a seminal work in this field of study. Note that we use one local step and global step pair. Our DARAP method is meant to be part of the forward pass in a larger optimization or a neural pipeline, and as such, we do not iterate the local and global steps as we do in classical ARAP optimizations. Instead, we just rely on gradient descent to optimize the deformation quantity, which is, in our case, per vertex normals, to attain the desired deformation in one pass. We adjust the lambda hyperparameter to allow the required strength in this one iteration. Here are some more results showing that we achieve a balance between preserving the structure of the shape while imparting medium to high frequency geometric content. For example, the cubified surfaces of the Lego shapes, as well as the bumps themselves representing the studs in the Lego style, while still preserving the identity of the source shapes. To tie this back to the topic of 2D supervision, what makes the supervision work so well? You can see in the renders that we use in the supervision that the silhouette and the shading are natural cues that directly come from the underlying geometry. And so an objective based on render images like this with shading is a lot of information when backpropagated to the 3D optimization variable. Moreover, small changes in the geometry produce small changes in these parts of the render thanks to differentiable rendering, as Dale mentioned earlier. Moreover, the ARAP's rotation-based representation decides the desired solution space for the task, which in our case is identity-preserving geometric stylization, and the linear solves smooth out the noisy SDS supervision. Notably, in other methods such as 3D paintbrush or other works, we also find that neural fields or MLPs defined over 3D coordinate space also act as a smoothness bias rather than linear solves. And so it turns out that this formulation has more going for it than just stylization. If you extend the optimization variable with a scale parameter in addition to direction or rotation, and crucially also do remeshing once in a while, which works really well with this vertex-based parameter, you can get some really nice geometry growths too instead of just stylization. And this is our new paper rad mesh, which you can look forward to in ECCV'26. I'll quickly hand it over to Dale to talk about some other general notes on optimization problems for generation.
Thanks, Salman. Yeah, so building off what Naman just talked about, sort of zooming out, it's clear that optimization, works really well for these generative approaches. And it's kind of interesting to think about, like, why is it actually the case? So we're arguing that it's because most of these generative methods typically share the following key properties. So one, they are naturally visualizable. So like things like colors, geometry, you can very clearly render and visualize. And then two, small changes in those 3D quantities result in smooth interpretable changes in the visualization. So again, these are the key things that you want to have for whatever you're trying to optimize. What are some of these visualizable qualities? So for things like stylization, like we just said, you're directly showing RGBs. And like, why does this work, right? So like, if we want to take a surface point on this human mesh and like turn it more red to be more like Iron Man, we can very easily sort of like interpolate those colors in a smooth way to get that color, the target color. And then for deformations, like Naman just talked about, like, with proper, shading and lighting, you can get like very clear like semantic differences in the renders when you actually change these geometries slightly. So again, like the key thing that we're sort of landing on is that smooth visualizations result in a much easier optimization and make these methods successful. So what if we want to look a little bit beyond generation? Can we do something with more analysis or some sort of different kind of optimization as well? And if we want to do this, like, can we apply some analytical qualities? And then also, like, will we be able to like have smooth visualizations of those analytical qualities? So maybe for something like segmentation, can we do that? So the first thing we need to figure out is, like, again, a lot of these generative methods, they rely on the fact that these 2D models understand a lot about generation, right? We know that these 2D models, these image generators, can generate images according to some text prompt. But can we do the same thing with something like segmentation? If you look at some of these generative results, you can see that they demonstrate a lot of semantic part understanding in their things. So if you do like Steve Jobs, you can see it puts like the facial hair on the chin, it puts the shirt folds above the waist, and also the pant creases on the thigh. And then while there's no explicit segmentation here, can we tease it out with some way we can visualize and optimize? So how do we do this with localizations? So again, the other thing we just talked about is we need this to be continuous, right? So segmentations are typically discrete. So we need some way to represent the segmentation continuously. That's not very hard. So the first thing we do is we just learn some network that takes in points on the surface, and it outputs a continuous probability of that point belonging to the segmentation we care about. So we have this like P and this 1 minus P. And then what we need to do now is we need to have some way to visualize this quantity in a way that's going to make sense for the generative model. So it's really simple. We just take like two predefined colors, and we just say, the higher the probability, the more yellow, and the lower the probability, the more gray. And we just have this probability weighted blend. And then we color the shape accordingly. So like maybe here we have some segmentation of the top of the head. You can see that like the coloring of the shape, this visualization, is entirely dependent on our segmentation. So in order to things to like look right to the generative model for our sort of visual loss, the underlying analytical property also has to be correct. And that's sort of what we're trying to like design our optimization for here. So you can see some of the results from this. It's kind of fun. You can like get these like really weird like segmentations on things that like don't actually exist. So like poncho on a horse, or like a necklace on a person, or headphones on a bunny. And you can also go like even crazier. So you can get things like a necklace on a lamp. And again, the reason this works sort of ties back to this idea of feature space similarity that we talked about earlier, right? So the way this approach is working is it's taking, renders of your 3D visualization, or your visualization of your 3D shape with your localization, and it's comparing it in feature space to some text prompt. And because of that, you can sort of get the best match, even though it doesn't actually exist, which is kind of fun. And so with that, I'm going to hand it back to Naman.
So to recap, optimization-based methods, they allow distilling the deep understanding of large 2D trained models back to 3D. And with this setting, aggregating multiple views and sharp boundaries, which we'll see come up later, are largely not concerns, since they are actually usually smoothed out over the many optimization iterations. However, their disadvantages include the Janus effect, since the context of views accounted for during one iteration don't apply to other iterations, causing these doubled faces and other such view-dependent artifacts. And there's also the major drawback that they're really slow, since they require backprop through not just the differential rendering, but possibly other large models, and require many, many small update steps to converge in a stable way. And so that brings us to the next set of techniques, which we categorize as back projection based, because as the name suggests, these methods take 2D signals and directly aggregate them in 3D, rather than optimize parameters through differential rendering and gradient descent. These methods have come out of the recognition that explicit surface is often sufficient to guide the organization of these 2D signals without the need for expensive backpropagation through differentiable rendering. We can classify back projection-based techniques by what sort of quantity is being brought from 2D views back onto 3D. Methods that do this on RGB values rely on 2D priors doing denoising or generating multi-view image directly in RGB space, usually to get a specific texture on the mesh. Methods to do this with deep features usually aim to cast the 2D prior's spatial knowledge onto 3D shapes for further downstream 3D geometry processing tasks.
Hello, hello, hello. Oh, I see. Okay. I could also just speak loudly. I don't think it goes on the hat.
Oh, sorry. Try this again.
This is our live technical demo. All right, thank you. These mics are very complicated. Hello? Hello? Okay, we're good. Awesome. Yes, anyway. Yeah, so Namian just introduced this sort of general space of back projection methods. So first, let's talk about what exactly back projection is. It's very simple. It basically, at its core, involves a direct mapping from 2D to 3D. But you might be wondering, like, but we already got that 2D to 3D mapping from differential rendering. Well, the difference is that differential rendering will be able to give you that mapping in the form of gradients. But in the case of these set of techniques, we're actually interested in something a little bit faster that we don't have to necessarily optimize parameters for, but actually just like take those 2D values and like really just stick them back onto the shape. So again, how do we do that, right? We need a mapping from 2D to 3D. That's not just a mapping from gradients to gradients. And thankfully, for any of you who've taken like a graphics 101 class, we actually get that mapping for free. Because thanks to the rasterization process, we, in rasterization, every pixel already undergoes sort of this containment check where we check whether it gets covered by a triangle. And from there, or in tandem, we compute barycentric coordinates for those pixel values, right, which are used to interpolate various vertex level qualities, such as colors in the case of a standard rendering. But the wonderful thing about these barycentric coordinates is that we can use them to interpolate any quantities we want from the vertices, including vertex positions. So as a very basic setup, right, we can define this function p, which takes as input some ij coordinates from our image, from our render space, and basically what this function will do is it'll take the pixel ij and give you back your 3D position from that pixel. And that's literally just defined as the vector matrix product of your barycentric coordinates with your concatenated, or not concatenated, but stacked vertex positions. And sort of a maybe underutilized but important for our application property of this type of barycentric coordinate-based parameterization is that even if we subdivide this triangle or we remesh it in any way, and we redefine our barycentric function based on those new triangles, we're going to get back the same exact value for this function, right? It's just going to be in terms of barycentric coordinates of a subdivided triangle, but again, the 3D position stays exactly the same. And yeah, so this is going to be important for us because we're going to end up taking advantage of this later to back project quantities in 3D that are entirely discretization agnostic. Okay. So another way to think about this is about renderings in general is that you can consider rendering as a surface resampling method, right? We take some discretization of the surface, we project that into pixel space. Now the pixels themselves will redefine where your surface is being sampled. And yeah, and just to reiterate, so now the number of samples we're receiving from the surface is determined not by the discretization, not by the vertices, but by the render resolution itself. Yeah, just to reiterate this point and also show off this visualization, we get this mapping for free. There is literally nothing that we need to do after rendering the shape, right? We get those barycentric coordinates, and we could just immediately map back pixel values onto the shape. Okay, so are we done? Unfortunately, not. One potential issue here is, as mentioned earlier, is what if you don't have features at the pixel level? Right? And this is actually an extremely common case. because in reality, most modern image encoders, and I would actually argue all image encoders that are basically, the most powerful or relevant these days, do not give pixel level features, and that's because of compute constraints. So image models will typically downsample in two different ways. They'll either just patchify the image, so in this case, they'll take some input image, generate patches for it, and then give a feature per patch. And this is sort of common among basically like any sort of transformer model these days, or diffusion transformer model. So the patchification is the go-to tokenization for those transformers. In the case of models such as variational autoencoders, or VAs, or UNets, they are something, they basically are entirely convolution-based, but even then, you're going to be running your input resolution through downsampling convolutions to get lower spatial resolution features on the downsampled image. So in either case, in order to actually get back values per pixel, we're going to need to upsample in some way. And of course, with upsampling comes aliasing. So let's look at a specific example. Let's take, for example, this render of a 3D model. When we pass it through some image encoder, and let's say in this case it's a VIT, so it patchifies, we're going to get a feature per patch, which is why you get this sort of like blocky looking PCA image. And yeah, so and in particular, you can see how like the patchification is starting to blur the boundaries between the ring geometry and the sort of the stuff behind it. And it causes the feature assignment to be blurred around that area. So how can we fix this? We actually can still recover the sharp boundaries of that ring feature with, surprise, surprise, another 2D model. Specifically, we could take some off-the-shelf segmentation models. So here in this case, we're showing segmentations produced by Meta's segment anything model. So basically what we can do is we can sort of run some generalized segmentation method, cast the segmentation groupings back onto the original feature image, and then basically just compute some statistics over that group. And from there, basically just take the outliers, apply some heuristic thresholding, and substitute the outlier features with the mode of that feature distribution within that cluster. And voila, you get back nice, clean features for your ring geometry. Yeah, sorry, oops. And of course, this assumes that you actually want common features for that geometry, which I think is, not a terrible assumption. Okay. So we've talked about how to get pixel level features. We've talked about how to get those features from pixels to 3D in a very clean way. But we're still not done because we still need to deal with the ever-present problem of multi-view inconsistency. This is very long-standing. We're not the first one to talk about this, or neither the last. And yeah, it's there's a lot of applications for methods that deal with this, from reconstruction to the kind of feature transfer we'll be talking about. So in the context of feature back projection, though, there's basically been three primary approaches in terms of aggregating them, and they mainly differ by the choice of control storage structure. So the most naive version is just to store them back onto vertices. The next is storage in the form of a UV map, and lastly, storage in form of a neural field. So, and these are by no means the end-all be-all of these storage structures, but these are sort of the most common that we've seen over the past few years. So let's go through each of them individually real quick. So in terms of vertex aggregation, it's pretty straightforward. For a given vertex, basically what you're going to do is you're going to check the pixel that corresponds to that vertex, assign that feature back to the pixel. Right off the bat, you can already tell why this is maybe sort of problematic, because the only pixels in any given render that contribute to a particular vertex is going to be one pixel at a time. And so And essentially, back projecting back onto pixels is actually going to tie your sample count back to your mesh resolution, which is exactly what we were trying to avoid to begin with this whole like barycentric setup. And so this comes with a few issues beyond simply just the single pixel per vertex issue. We end up having to throw away a lot of the signal that we're actually getting from our rich image models, right? And we want to take advantage of that. So in this toy example, right, I visualized a 8x8 render around this torus shape, back projected those pixels, and grayed out all the pixels that don't actually correspond to any particular vertex because they don't cover any vertices on that shape. And what you'll see here is that like over 50% of that signal is being thrown away. Right, and this is only for an 8x8. The proportion will naturally get worse as your render resolution increases, and your pixels get smaller, hence covering lower surface area of the shape. Okay, so vertices not so good. Let's talk about UV maps. So in this case, let's assume we already have some back projection mapping that goes from this like colored render back onto the surface. In this case, our surface is this 2 triangle setup. From here, you can compute a UV parameterization, which, if you're not familiar, is basically some injective mapping from 3D to 2D. The primary difference between this and the render is that the whole shape is represented in this image space, in this UV space. And basically, when you sort of collapse these maps, you're basically getting a map from 2D to 2D. And yeah, your back projected values can then be stored onto the textual coordinates of this UV map. And so the nice thing about this is that, once again, you're storing values at pixels, which is generally less lossy, more memory efficient than storage at vertices, and you're not having to deal with any kind of sort of sampling issues or discretization issues or irregularities of the surface itself. Okay. Unfortunately, this also comes with some downsides, primarily that now the quality of your storage is going to depend on your textile density. And what that means is how much surface area the actual shape each UV pixel occupies will completely determine what kind of loss artifacts you're going to experience. So for example, in the image on the right, oops, sorry. What is happening? Oh. Yeah, anyway. For example, in the image on the right, you know, your textile density is quite low there. Therefore, you're only going to get a very small portion of that colorful texture, let's say you have on your triangle. Okay, so past works that have leveraged this representation for feature storage have mostly largely been for texture applications, which is unsurprising, such as text-to-text or texture. And they've also incorporated sort of an additional visual heuristic to make their aggregation a little bit more, let's say, visual conditioned. Specifically, they take note of the fact that when you have shading, you can sort of use the shading will cause your albedo to be sort of represented with some noise. And so what they do is they incorporate a confidence scoring based on the shading parameters, specifically the angle between your surface normal and your camera ray direction. Basically, the intuition here is that parts of the surface that are oriented away from the camera provide a lossier color signal because of, again, shading. And so pixels with normals facing directly the camera or closer to the camera ray direction should be more reliable indicators of the object's true diffuse color. And so these works tend to sort of aggregate color signals from generative diffusion models by iteratively rendering and painting their UV maps in some weighted way based on the surface normal information. Okay. So lastly, let's talk about neural fields. Neural fields are actually a really great way to store features because really they can store features at arbitrary surface coordinates in a near lossless way. The general idea behind them is that you can use MLPs to parameterize a smooth field in 3D ambient space. And how these neural fields are trained is you can just take your Cori coordinates, which you already have 3D positions for, and basically send those into some ML neural field, which is parameterized by an MLP, and supervise them with ground truth feature quantities that you've defined at those pixels. And so the power of these neural fields is primarily in the representational capacity, which is able to both accurately store features at arbitrary coordinate locations, and they'll automatically simultaneously resolve multi-view inconsistency through smooth interpolation learned through the network optimization itself. So this is just like a common feature of MLPs that has been exploited for forever at this point. And as mentioned, these neural fields are functions parameterized over ambient space, so your 3D coordinate space, which means they're actually not restricted to any particular surface discretization, much like the render itself. And so what does that imply? There's actually a lot of really great properties we can exploit from this ambient space property, and in particular with dealing with 3D objects. So for example, feature fields are representation agnostic and hence can be transferred across both different remeshing and representation, different remeshings and representations. So one particular application we take advantage of in our deep feature deformation weights paper is the fact that we can first, if we want to distill features onto this Lucy model, which is 28 million triangles, we can first downsample it by, what is this, like 99%. And before rendering them for our distillation. And this is actually really nice because, sorry, let me just finish this animation. Yeah, and this is really nice because shapes with several million triangles can easily run into memory errors on consumer-grade GPUs. But in our case, because we're first distilling these features into a neural field, we can distill at any resolution we want of the underlying shape, but query at the original resolution. And we still get meaningful features because thankfully with these really large shapes, when you coarsen them a lot, you actually don't get much reduction in the visual fidelity, which is exactly the signal that these image models are using to provide you your features. Okay. And I mentioned transfer across representations, so we can see that with, for example, let's start with the triangle mesh. We do that distillation. And we now can sample that field that we trained with the triangle mesh with various implicits, such as Gaussian splats, neural radiance fields, point clouds. And thanks to the nice interpolating properties of these neural fields, we can query these representations with things like volumetric array casting in the case of both NURBS and Gaussian splats, and we'll still get reasonable features back. Okay, there's more. So we can show sort of off-surface evaluations for symmetry detection as well with this neural field representation. So again, in the DFD paper, we show something that we call like visual symmetry detection. Basically, how this works is you can take a shape that clearly has no extrinsic symmetry or even intrinsic, because of the high frequency details in the folds of the cloth. But as people, we can clearly see that there is some sort of symmetry going on. So how do we capture that symmetry, right? We actually do something very, very simple, which is for a given candidate symmetry plane, you can sort of take either side of the shape and reflect them across that plane, and then query the feature field at exactly those coordinates, because again, we have a feature field that gives reasonable features even when you're querying off the surface, because it's defined over ambient space. And so we can establish feature correspondences for both reflections and then validate this symmetry plane. Yeah, and as I mentioned, this sort of symmetry is not necessarily captured by extrinsic or intrinsic symmetry, though I will note that maybe if you ran some sort of low-pass filter on your intrinsics, you might be able to capture this. Okay. But wait, there's more. We can even use the feature field to conduct texture space queries. in which the idea is to sort of find out what texels or pixels in the texture image can correspond visually, will correspond visually to a particular query point. So in this case, let's say we, choose a point on the beak of the owl model, and what we want to figure out is some segmentation of this really nasty texture image, like where the textures actually correspond to this beak. And yeah, so clearly you can see this is pretty hard to do because these texture images are typically highly fragmented packings of the surface geometry. So with the feature field, of course, we can establish a direct correspondence between each texel and a deep feature. And how we do that is we can first rasterize a position map using exactly that UV mapping that we have from the model. Query the feature field with those rasterized position map features to sort of get back a feature map, which I haven't visualized here, and then sort of run some sort of feature similarity check between the point queried on the beak and all the features we've just rasterized in our UV space. And from here, we can just threshold and segment. It's a little hard to see, but basically, from there, you can see sort of the parts of the texture image that are outlined in purple that represent all the textures that actually go on that beak. Okay. So we've seen a ton of applications already for 2D features for 3D tasks. Some other ones not yet mentioned include implicit surface editing, generation, more traditional tasks like segmentation, correspondence, and classification, and deformation. And surely, yes, and surely there will be more to come as vision models become more powerful. But for now, I want to drill in a little bit into this deformation application. It's my paper, so I'm biased, but also because I think it involves sort of a relatively unintuitive application of image features with some surprising consequences. So let's take a look. So the basic motivation behind this deep feature deformation weights method is basically to see how we can incorporate 2D priors into a linear blend skinning model. For those who are unfamiliar, linear blend skinning is just a pretty classic and simple method for interpolating deformations assigned to low-dimensional control structures. For interpolating those deformations to a higher dimensional surface representation, such as a triangle mesh. This is a linear blend skinning equation. So V prime and Vi are the deformed initial vertices, respectively, and we have deformation matrices D assigned to K control structures. And W here is the matrix that stores those linear blending weights. And control structures in this case is a deliberately vague term because they can be basically any kind of lower dimensional structures such as points, region handles, skeleton rigs, cage nodes, etc. You could even have virtual control structures which are not represented in 3D space at all or simply floating in abstraction space. But in this work, we basically just focus on the simplest kind of control structure, which is a point handle. And so one more note here, just because maybe some of the rigging people or animation people are starting to pull out their pitchforks. The weights will sometimes be used to blend control structure positions rather than deformations. And linear blend skinning typically refers to the blending of deformation specifically, but for simplicity's sake, I'm just going to be collapsing that distinction. Yeah. Okay. And so with all those caveats aside, really what we care most about in this setup is the weights matrix, because W essentially parameterizes that deformation subspace for our 3D mesh. So a lot of attention in past works have gone towards different ways of getting these weights. But one common characteristic of all these previous methods is that to compute the weights, you need to solve some optimization problem, which is a function of your control point set. And what that means in practice is if you want to, let's say, add or delete or update your control structure set in any way, you have to resolve the optimization. And you can see how that can get expensive pretty fast for, let's say, interactive applications. Okay. So in deep feature deformation weights, we do something very dumb. You see a common trend here, which is we just assume every surface point can be a control handle. And so what does that mean in practice? That means that we can define our blending weights as just the L2 distance between a feature at a vertex on the mesh and a feature at your point handle of choice. And in this case, where phi in this formula is some feature field that you've distilled, and HK is your point handle, which can be off the surface, on the surface, wherever. Okay. And yeah, the important part of this function is that it's really fast to compute. The addition of a new handle involves just another feature field query and an L2 evaluation, which for most meshes can be done in real time. Okay. So there's a few other constraints I should mention regarding these weights, but they're quite few. We have to assume unit norm features so that we guarantee the weights are between -1 and 1. And we also clamp negative weights to 0 because negative weights result in unintuitive behavior. But once we have that, we're basically done. And so the intuition behind these weights is that points with similar visual features should co-deform. And it turns out they actually work surprisingly well. I was surprised at least. And so if you visualize the weights for corresponding point handles on this like hermit crab shape, for example, you can see that essentially what these weights are doing is a soft semantic segmentation of your shape corresponding to your point selection. Okay. And so because these weights are computed quickly for arbitrary surface handles, we can apply them in some real-time click and deform workflow as shown here. The user simply needs to define some appropriate transformation per handle, and the shape itself will deform in some meaningful way. Let's say semantics and symmetry preserving. And again, this is just thanks to like the visual prior encoded in image features. Okay, so of course this method comes with trade-offs, especially when compared against the previous work done by traditional optimization-based skinning methods. So, for example, we don't guarantee any kind of partition of unity or linear precision. And this property is typically enforced to guarantee, for example, the same deformation is applied. If the same deformation is applied to every handle, the deformation is perfectly reproduced across the surface. So in the case of a single handle translation on this chair, you're just going to pull that whole chair down. But on the other hand, single handle transformations maybe are desirable. And that's sort of what we enable by sort of sacrificing this property. Okay. Another one is that we don't make, another sacrifice we make is in our regularization, which is most namely that there is none. And so if we look at traditional methods like ARAP or biharmonic coordinates, which optimize for some local rigidity energy, this is going to ensure that the shape volume is preserved through deformation and surface distortion is minimized. In our case, we make that trade-off in order to first allow for real-time control point updates, which is referencing that click and control deform workflow. And we sort of allow for unconstrained deformation so that we can stretch, scale, and generally distort the shape, which sort of is serving a different need, let's say. And you could sort of qualify this in terms of ARAP style deformations are useful for something like a physically plausible animation workflow, whereas maybe a user may want DFD weights for something that's more like a shape sculpting application. Okay. So of course, another limitation here is that we have to optimize a feature field, which comes with an upfront fixed cost. But as noted in our back projection slides, feature field optimization is completely discretization agnostic because the surface is sampled through rendering, resampled rather. And so what that means in practice is that our, getting feature fields for this shape is essentially fixed across all mesh resolutions up to IO and decimation operations. So we actually perform an empirical experiment by timing our distillation on a data set of over 6,000 shapes ranging from 1,000 to 10 million faces. And the distillation will scale basically sublinearly, and any additional extra time spent in that upper scale is basically attributable to I/O operations and the simplification algorithm we apply. Okay, and as we've sort of seen already, having a feature field comes with a lot of perks. And in the case of deformation, like I showed before, you can sort of take your feature field, sort of, re-represent your shape in a variety of different sort of representations, throw them back into your feature field, apply those same deformations, and get back basically the same result. Okay. And finally, I would be remiss to not mention that, of course, these weights are entirely determined by some black box image model, which can encode all sorts of mysterious priors. So in practice, we've seen that they work generally well and are robust, but can also produce some pretty interesting but undesirable correspondences. So in this case, we took Dino3 features and put them on Spot, and it actually seems to do some sort of texture segmentation on the spots on Spot, which I thought was interesting. Okay, so we've talked about these two different quantities that have been sort of addressed in the back projection literature. And the key thing that combines both of these two themes is that these are quantities that are invariant to the projection itself. And so one thing that we're sort of interested in is this other domain of quantities which are not necessarily invariant to the projection operation, namely geometric quantities, such as, let's say, image space gradients. And yeah, this space has been pretty virtually unexplored, but there's certainly potential here for some interesting work, I think. So let's see. Let's take, for example, this render of Spot. And let's say we took this render and we used some generative model to edit this image, in this case, putting sunglasses on Spot. So in the case of the sunglasses, we can actually, if we compute the image gradients over the shape, what we're going to find is that the image gradients in the center of those glasses lenses are going to roughly prescribe the geometric extents of your glasses frame. And so one thing you could do now with those image gradients is to not only perform your traditional back projection by mapping pixels to 3D, but you would want to simultaneously unproject the gradients themselves, so apply an unprojection operation to the gradients so that they can be properly mapped back to your local surface. And let's see. And yeah, so since these gradients prescribe the rough geometry, you could say the geometric extents of these sunglasses, you could feasibly maybe use them for, let's say, reconstructing the frame of the glasses on your original surface for a more accurate surface, a more accurate object reconstruction, for example. This is just some one random idea that we toss around, but I think there's a lot of room for different applications for this type of image space geometry back projection. Okay, so now we can conclude. Basically, we've seen a lot of different applications of 2D priors for 3D tasks. We've sort of distilled down the prereqs for, let's say, when these 2D priors may actually be useful. Specifically, they're useful when 3D data is scarce, as Dale has mentioned already. They're useful when the objective benefits from sort of visual reasoning. So of course, generation, texture synthesis, deformation, all of those sort of involve some sort of visual criteria. And as Dale mentioned as well, the quantity can be visually represented. So again, that doesn't necessarily apply to just the obvious quantities such as colors and geometry, but it can be something like segmentation probabilities, again, as Dale has described, or something else entirely. that's up to future work. Okay. And yeah, so of course, it's not going to be relevant for all tasks, but as you've seen today, these 2D powers can be very powerful when leveraged properly and applied to the correct domain. So with that, thank you very much.
Come on. Thank you.
So when you're visualizing kind of abstract information like these segmentations, how much does it matter how you visualize it? Like, will it work way better if I use a blue highlighter than a yellow highlighter?
That's a great question. So we actually we looked into like exactly that basically because we our first thought was like you kind of want to like try as many things as possible and like just like maybe every iteration you like sample a new color and you update the text prompt accordingly. And we found that like again we're just completely at the mercy of these 2D models. And like if you think about like the priors that these things have seen in terms of the data they've been trained on, it's seen maybe more images with like a yellow highlight because that's like more in the data distribution it would have seen. And it seemed like we have some figure in the paper that basically shows it works better with that than like with other colors. But yeah, that's a good question. Like, and I think we thought the same thing. Like, you know, is there any reason why like yellow specifically? And a little bit better, but it's not. It still kind of works with other colors. But yeah.
I had a question about the. So when you optimize the neural feature fields on mesh, you sample the points on the triangles, and you also show that you do this simplification. So sometimes the triangle that's simplified can be removed a lot from the original geometry, and then the interpolation away from the original surface, is that sort of just a lucky coincidence that the MLP sort of interpolates away from the surface, or do you make sure that it is correct in some way?
Yeah, we don't regularize for that at all. So basically the assumption here is that when you decimate, your shape will look sort of visually similar to the original resolution. Of course, it may be possible in cases where you have a extreme sort of deforming of your original geometry that still looks the same from a render. I personally don't think that case comes up very much. So yeah, basically the idea is that as long as you decimate to within like reasonable preservation of visual fidelity, you're going to be getting back good features. Yeah.
You can keep the microphone.
Oh, try it. Okay.
Thank you for tonight's talk. I have a question about the representation. So your works were mainly about like shape deformation, where you assume that you have a mesh and you're optimizing the geometry or the positions of the vertices or the textures. But like if you were to do shape generation rather than deformation, do you think the mesh is the right representation? Because mesh is kind of hard to generate because you have to start from, you have to get the connectivity right. So I wanted to ask you what your opinions on that was.
Yeah. Wait, you can go first.
My thought is very short. Yeah, I think it's like, yeah, I think definitely mesh generation is a lot harder. I think like we've seen some like approaches recently that they just have a lot more data than they had even like 2 years ago. And I think like you could see some of these autoregressive approaches for generating meshes like being very successful. But I think like definitely in terms of ease of generation, an implicit representation can be much more easy, like a nerve for Gaussian splatting or something like that. Yeah.
Yeah, I mean, this is like sort of the $1 million problem, and if you solve it, I think you'll win a lot of prizes at the very least, if not money. And the fundamental tension here is that implicit representations are somehow very well optimized for visual recovery of the shape, but of course, you don't get back much of the geometry at all. And so, whereas meshes obviously allow you to start with some discrete, well-defined structure, and thus allow you to sort of constrain, how do I put this? They give you some constraint on the starting topology, basically, and so sort of the $1 million question is how do you seamlessly map between those two representations? And yeah, I think that's an open question. But it is true that I think, as of right now, explicit representations have been notoriously much more difficult to try and learn neural networks over. And yeah, not sure why.
Thank you. So my question is about local fine-grained control or editing of the 3D model cases. So I was wondering, having 2D image priors causes a specific limitation, or it's fine for that purpose? So yeah. Yeah, let's, in simple case, let's say you want to specifically modify a small area, but in a fine-grained manner. So I was wondering, since the 2D image-based priors are for general purpose images that you mentioned, loads of data is available. So I was wondering, is that a limitation for this 3D modeling and local fine-grained editing or not? So yeah.
Yeah, I think it's a great question. I think like if you're just trying to like optimize something without any kind of regularization or anything like that, like from the images directly, that can be very hard. Like if you think like, if you tell like an image generator, even like getting like image editing to be like perfectly localized is very difficult. And it's getting better and better. But I think like, again, like one of the paper on like the CSD loss, that was sort of like a part of it, but the main point of that paper was actually to do local editing on meshes. And it sort of combined the idea from the highlighter, where you first like sort of find some explicit localization on the actual geometry itself. And then once you have that localization, you can sort of constrain your texture generation to be within that region. So I think, again, the approach we took to that was to like, yeah, first find the localization in 3D. And then like once you have that, you can like force it to be constrained to that area. Whereas if like, again, there are a lot of other approaches that do also try and do 3D editing. And a lot of times they do it sort of, again, just based on these priors, and there's not as many guarantees about like where you are or aren't editing. So that's definitely a consideration. Yeah.
And also, can I add something? I think in many of these tasks, part of the contribution is designing the sort of harness around the 2D model supervision to only edit what you want on the 3D shape. So in Dale's case, it's like the mask. You get the mask from 3D highlighter. And in the case of deformations, you can you can by construction restrict the solves or the deformation like displacements to only happen on the area that you care about. And so that structure is what helps you rein in all this like vast data prior of these 2D models to only do what you want it to do, which can still be hit or miss depending on how you prompt it. But that's the beauty of like imposing extra structure on top of these tasks.
Looks like that's it. Let's thank our speakers again.